Yes, you are audible, Shanshu.
Okay, thank you. So, good evening, everyone. Welcome to our webinar on shaping and sensing of light fields. I am Shanshu Mishra, Vice Chair of IEEE Sensors Council, Student Branch Chapter, MNIT Allahabad, Prayagraj. It's a pleasure to have you all with us today. The IEEE Sensors Council Student Branch Chapter stands as a vibrant community of budding engineers committed to propelling sensor technology forward. Here, at the heart of MNIT Allahabad, we are not mere enthusiasts. We are trailblazers in the field of sensor technology. Through a spectrum of activities such as seminars, webinars, workshops, and collaborative projects, we continually push the boundaries of what's achievable in sensing applications. Over the past few decades, the field of optics has seen tremendous growth, especially in the shaping light fields for various applications. Structured light, with its precisely defined spatial properties, has become crucial in areas such as biological specimen manipulation, material processing, and advanced information systems. To guide us through this fascinating topic, we are privileged to have Dr. Praveen Kumar from IIT Bhilai as our keynote speaker. Dr. Kumar is an assistant professor in the Department of Physics, specializing in applied optics. Dr. Kumar's impressive academic journey includes a PhD from IIT Patna, postdoctoral fellowships from the University of Houston, USA, and Chiba University, Japan, and several prestigious awards, such as the KVRSS Research Award and the OSI Best PhD Thesis Award. He is an active member of renowned organizations like the Optical Society of India, Optica, SPI, and ARVO, and he has also published numerous research articles in top international journals. His research focuses on light shaping and sensing techniques and their applications. His work in structured light, including the development of Laguerre-Gaussian beams and vector beams, has made significant contributions to the field. These advancements, these advancements hold potential for breakthroughs in data processing, communications, and cryptography. Without further ado, please join me in welcoming Dr. Praveen Kumar. Sir, you can continue now.
Okay, so hello everyone. So I hope my voice is audible to everyone. Please confirm this.
Yes, sir, you are audible.
Yes, sir, you are audible.
Okay, thank you. So first of all, many thanks to the organizers, especially Deepak sir, for providing me this opportunity, right, to talk something about what I am very interested in and what I am doing at present. So the title of my presentation today is Shaping and Sensing of Light Fields. Okay. So I started working in optics from my MSc, and then I moved to different institutes for my PhD, postdocs, and now I'm working in IIT Bhilai. And my research activities is mostly light shaping, light sensing, and then I see some of the applications of the techniques which I use. Okay. So in today's presentation, I would mostly describe maybe some techniques of light shaping, sensing, and some of the uses in information optics and medical optics. So this much today I will try to describe. So very precisely, I will talk about the special light modulators which we can use to control light. And light shaping, one of the example is optical vortex, and its vector form is polarisation engineer optical vortex. So these two I will describe today, and then how we can use it for some of the applications. So this is the outline of my today's presentation. So my area of interest is optics, and as you all know that optics is a branch of physics where we study the behavior and different properties of light, right? So this picture, I hope you must be very familiar with. So this is famous TIR, total internal reflection, right? So there are many interesting properties of light. And first of all, even this is interesting, like what is light? Even there was a lot of debates in physics about light. One of the famous debate was between whether the light is a particle or a wave, right? So there are many interesting talks. So when I started working in light, I wanted to understand its properties, sources, parameters which we can use to describe it, how we can mathematically represent it, and then how we can use it for our different uses, like in different areas, how we can use it, right? So the recent, or we can say the most established definition of light which we have today is that light is the electromagnetic radiation that can be perceived by human eye. So this you can see in most of the textbooks, they use this type of definition. And of course, without light, there will be no life. So sun is the source of light, and there are many kinds, like different colors. Light can be of different intensity, different wavelengths. Okay. So there are many interesting aspects of light. And how my journey started, it started from the photonics lab of NIT Jamshedpur, where I started my MSc. So we were the first batch there, and the optics lab was not very established. So we devoted a lot of time to not only to just do the experiments, but to establish the setups, right? So you can see there are many, like the lab was not very like have modern equipments, all were very outdated one, but it was very good to learn. So I spent a lot of time there, and that's how I got very interested in playing with light, with different kinds of laser beams, and then experiments on interference, diffraction, polarization. I think you must be familiar with, and you have also done this kind of experiments like Newton's ring experiment, right? So I was very much interested and very happy to doing those experiments. And then I decided for my other like for future, like for PhD research, I want to go in optics. So I was very determined to work in optics since from my MSc. And for that reason, I went to IIT Patna, and there you can see the lab was very good. I got many good new tools to play and to control light. So it was like my dream come true to being into the optics laboratory of IIT Patna. And he was my supervisor, Naveen Nishchal. Okay, and they are the and rest of them are my colleagues. Okay, mostly my seniors. So I learned many things there in optics. So the question which I started for my PhD research is this: are conventional laser beams adequate? So I think you must have seen laser pointers or maybe other kinds of lasers. So the beam which these laser pointers produce, if you see carefully, the intensity distribution would be like this, right? Center would be very bright, and as you go uh, far from the center, it will decrease, and we call it Gaussian distribution. And that's why we also call it Gaussian beams. So when I say conventional laser beams, I am referring to Gaussian beams. So when the laser was discovered first time, and most of the optical systems which are using lasers, they are mostly using Gaussian beams, okay, which have this kind of intensity profile. But now we know that science is advancing, and our needs are also growing. So these conventional Gaussian beams, are they adequate for all kinds of needs and applications we are doing now? So of course, no. Okay, there are many requirements which are coming up. So what other options we have? So to know what other options we have to see carefully how light is and how we are describing it, right? So, so being working in applied optics, I see these parameters like intensity, wavefront, polarization, wavelength. There can be others also, but for a general optics person, these parameters are very important, right? Intensity and this wavefront, polarization and wavelength. And these are very basic parameters. So now our aim was to go beyond the Gaussian beams, which means we need to control these parameters, okay, in degrees of freedom. Like mean whatever degree of freedom which we can achieve and we can control it, that was our main objective. So what people are doing is they are shaping the light in a spatial domain. It can be controlled either in space or in time, right? So recently people have seen that controlling the light fields, especially like in space, it can produce different types of light beams and with different unique properties. So this picture, it appears as Rangoli designs, right? But mostly they are the structured light fields and very established and well-known light fields. Okay, here you can say Gaussian beam also here in one of the this area. So this picture here shows that we can control light, okay, spatially and in many ways, right? So this is how I planned my research, that I will be working on this shaped light fields. I will study its types and properties and how we can generate it, and then how we can measure it or characterize it. So this will require light sensing techniques, and then how we are going to use it for different applications. So this was my proper way to research. Now, you must have seen this kind of water circulating in a circle, right? And when we see here that light going in a circular motion, in the center you can observe there is no water. Okay, so all water is in the corners, and we call this phenomena as whirlpool. And this can also be seen in air. Okay, with when there is cyclones, you can see in Hindi we call it bhawandar. So there is circular motion of this water, air, and this whirlpool is created. Okay. So this is a normal phenomena of vortex. Okay, even in astronomy, you must have studied about black holes. That is also an example of vortex. We also call it singularity in mathematical terms. So this phenomena can also be seen in light, right? So when the water circulates, it creates vortex. Similarly, when there is a rotation in the optical field, we get a vortex. Vortex means there is a no light at the center. Okay, light is all around it, but not at the center. It is an optical vortex. We can also call it twisted light beams, right? So I was very interested in this particular beam, optical vortex. Then I decided to work on it. And other motivation was this optical vortex is very important. Okay, why? One of the fundamental reason is when we talk about the momentum of light beams. Okay, so light beam or a simple, you can take a laser beam, so it can have a momentum, linear momentum also. Sometimes we call it radiation pressure, right? So, but going beyond the linear momentum, it can have angular momentum as well. And angular momentum can also of two types. One would be the orbital angular momentum, and light can also have a spin angular momentum. And it is very interesting to know that the orbital angular momentum is connected with the twisted phase, which is the optical vortex, whereas the spin angular momentum is connected to the polarization of light. And then we can use this momentum, we can transfer it to some particle or some materials, and then we can create some motion of certain structures, okay, using light. So material processing applications, optical tweezers, so these beams are useful there. And one more property is this optical vortex, they can have large spatial degree of freedom, which I will describe in my coming slides. And conventional to the Gaussian beams, suppose I want to use it for information encoding, then as compared to Gaussian beams, optical vortex will give me more degree of freedom. Okay, that's why people are interested to use these beams in optical communications, cryptography, and other information processing applications. And some of the applications can be seen in optical imaging because certain type of beams which have this optical vortex, they create non-diffracting features. All right. So then next is how we can generate this kind of beams. Okay, so then we need a light modulator. So this device is a picture of a light modulator. We call it SLM. S stands for spatial light modulator. Okay, so the phenomena is simple, that the wavefront which is coming, we can control its wavefront through this device using program MATLAB, Python, or any other programming software. Okay, we can control the wavefront, and then we can create desired wavefront of light. And then we have to carefully control these parameters like amplitude, phase, polarization. Wavelength remains same in most of the experiments until we are doing some nonlinear. These three parameters are important: amplitude, polarization, and phase. And these parameters are not independent. They are somehow dependent. So that we need to understand properly, that when we control phase, what is going to be in the amplitude and polarization. So that is the main thing to understand and to work. So this special light modulator, this is nothing but a phase shifter. In simple words, we can say it as a phase shifter. But phase shifter which have the spatial control. Phase shifting we can understand using this animation, that this picture shows in phase, and here it is phase shift of 90, or here it will be phase shift of 180. So this phase shift is, this SLM does this phase shift, but in every pixels. Okay, so this is how we create different amount of phase shift in different points of light. Okay, that's why we call it light shaping in spatial domain. Okay, and we control this phase shift using some gray level, which is an image in the computer. Okay, and then we can create desired front. For example, if you want to produce an optical vortex, we have to do the phase shift through this gray level. Okay, we call it, sometimes people use the term computer generated hologram, or sometimes we can just say gray image, okay, to create optical vortex. But when I tried to use this SLM for optical vortex, there was some errors, because this device, although looks simple, but the phase is very critical parameter of light, and there are many things to take care of. So when I try to produce the optical vortex, I see there were many errors coming up. Okay, so then I identified these errors which was coming, and then I did some methods to correct it. Okay, so that was one of my work during my PhD. Okay, so for that, I measured the phase retardance of light. Okay, so this was the grayscale pattern which I displayed in the SLM. My objective was to first measure the phase response of SLM, and then to correct it, to calibrate it. Okay, so I did this experiment, this setup here, and SLM has very important property that it modulates the light only in one direction. It means, suppose the light which is coming here, incident light, is, suppose it has two components like X polarized and Y polarized. But through SLM, we can control only one of the component, because SLM consists of liquid crystals which are birefringent, and birefringent allows us phase shift of a specific polarization. Okay, so and that will produce retardance between the light X and Y component, and that will change the polarization of light. And that polarization we measure through this other section, which is the Stokes polarimetry. Okay, measuring the Stokes parameter of light. And once we know the Stokes parameter, S2 and S3, we get the phase delay. Okay, so this is one example to measure the phase of light, okay, by using 4 intensity pictures, because the phase delay we cannot measure directly. Okay, suppose there is a laser beam and someone asks you what is the intensity, you can simply put a camera and then record the intensity. But if someone asks you what is the phase of light, then it cannot be measured directly. Okay, so that needs some additional techniques. So this is one of the technique. Okay, so this is the mathematical explanation what we did. So this the equation is it is in Jones matrix formalism, where we describe the polarization of light in matrix form. Okay, and this Stokes parameter, I think some of you may be familiar with this Stokes parameter. These are the parameters which we use to describe the polarization of light. Okay. So one more method to measure the phase of light is through interferometry. Okay, fringes. You must have seen fringes sometimes doing experiments or maybe in some other areas. Okay, so through interference also we can measure the phase response of SLM what we have. Okay, so we can use we can see the fringes. Suppose in a Michelson interferometer we have to see the fringe shift for different gray levels, and for different phase shift the fringe will shift, and by measuring how much is the shift in the fringes we can calculate the phase of the light, and this is the formula for interferometry, right? So through these experiments I calculated the what the SLM is doing. Okay, if you have some input gray level and what phase actually the SLM is providing to the light by doing both the method. And by measuring it, I found these three things, these 3 points which needs correction for it. So for correction, then I applied some of the methods like voltage optimization. One was the correction in nonlinearity, for which I made some algorithm for it. And one was the correction in spatially varying phase response by adding a compensation gray image to the SLM. And with these 3 correction, I was able to produce good quality optical vortex. We can see this is a simulated phase which I was expecting from the light, and this is what I got. And if the phase modulation is correct, we can also use it for amplitude modulation of light. So this is the optical image when the SLM was not calibrated, and after calibration we can see it is very close to the real image, right? And once after this experiment, the special light modulator was ready for producing different kinds of light, particularly for light shaping. Okay, so this is the some other examples of optical vortex which I produce. So this L equal to 1, 3, 5, 10. This represents the topological charge of optical vortex. Okay, which also means the amount of twist in the light. Okay, so this has only rotation of 2 pi. This has rotation of 6 pi. This has rotation of 10 pi, and this has 10 into 2 pi, that is 20 pi rotation. Okay, so with increase in the twist, the size of vortex increases. Okay, so and that is why in the initially when I was mentioning that optical vortices, they are used for optical communications, and that was only for this reason, because the amount of twist can be like any physical number, integral numbers. Okay, and this is unbounded. But if you compare with the polarization of light, so polarization is only 2 orthogonal modes. Either it can be x polarized, y polarized, or in circular basis it can be LCP or RCP, like left-handed polarized or right-handed circular polarized. Okay, so that has only 2 orthogonal modes. But in this case, with optical vortices, we can produce different numbers, different integral numbers. In principle, it can go from minus infinity to plus infinity, but in real life, in laboratory, we can easily produce up to like 100, minus 100 to plus 100. So it gives lot of degree of freedom. Okay, so this is one of the attractive applications. And also we can produce optical vortices in different positions of light. Okay, we call it optical vortex array. So after generation, next was that how we can detect and characterize these optical vortices. Okay, because I told you that phase cannot be directly seen by camera. Camera cannot record phase. So we need some indirect methods, and indirect methods can be through use of diffraction, polarization, interference, and wavefront sensors also that can also do phase estimation. Okay. So what I did is I tried method of interferometry. Okay. So now we can see here that this is the one twist, topological charge 1. This is the topological charge 2. So this picture denotes the wavefront of light. Okay, and this is the intensity. So in intensity, there is no significant difference between 1 and 2, but wavefront structure is significantly different. So that we have to know through interferometry. Okay. So I tried some methods of self-reference interferometry. Self-reference because for real applications, we may not have the reference beam available all the time. So whatever the beam is coming, we have to create a reference beam from there itself through different parameters. And then our aim is to create well-defined fringe pattern through which we can extract maximum information. So I tried different configurations through which this particular uh, fringe pattern, or we can say this particular configuration, uh, was very effective in producing in determination of high high value of topological charges. Okay, so suppose this is the beam intensity and this is the phase of it, so we can produce the self interference, this fringe patterns, and the number of, and by analyzing the fringe structure, for example here the number of discontinuous fringes can reveal this the phase of the light beam. So this is the way to determine it. And why we are interested to do it, because for any experiment where we are using optical vortexes in any like information systems, there we need to identify the topological charge, right? And these experiments can be done through Michelson, Mach-Zehnder, or simple other method, like other ways of lateral shear interferometry. Okay, so coming to the next thing, which is the polarization of light. So we can also, the previous slides, I talked mostly about the wavefront of light, how we can shape and control the wavefront of light. But now I'm going to talk about how to shape the polarization of light fields. Okay, so polarization, so this picture shows uniform polarization, means light is linearly polarized. But light can also have non-uniform polarization. It means light can have different state of polarization in different points. So common way to call it as vector fields. Okay, and this we call it scalar fields. So we can produce like different kinds of polarization in a light beam. And why? How we can do it? Because through controlling both the x and y parameters of light, because this polarization comes from this vector nature of light, right? Ex component and ey component. Then we need to control the wavefront of light of both these components. Then we can produce vector beams. And this is the setup which I did in IIT Patna, where we use this special light modulator to control this x and y component one by one. Okay, and there are some other wave plates to control the polarization basis. And this is the actual setup which we did. Okay, and this another setup is the Mach-Zehnder, which we used for the characterization of these kind of beams. Okay, so we can also use the special light modulator to control the polarization of light. Okay, so next is why now we see that we have used special light modulator for controlling the wavefront, polarization, right, and intensity we can control very easily. So all these three parameter, intensity, phase, and polarization, now we can control it. Okay, so then what other applications we can do? So one is the information processing or crypto systems. Cryptography, I think, is very well-known term. Even in WhatsApp, you have seen that your message is encrypted from end to end, right? So they use digital techniques for cryptography. But interesting is we can also use optical methods to encrypt any uh, optical information. So cryptography is basically a technique to encrypt the information such that any information is only the authorized person can uh, get back the information by applying some key, and any unauthorized user in between cannot have the access to the original information. Okay, so this is the basic concept of a cryptography. So we in one of the experiment we used this vector modes of light, okay, to encode multiple images at once in a light beam and then also to encrypt it. Okay, for example, these three images we can encode in the light beam through polarization. Okay, it means it is like this, that the light beam have different state of polarization in different points, and the rotation of polarization, you see that the beam has different angle of rotation. So this angle of rotation contains the information about the information which is encoded. For example, 45-degree rotation would represent some information, 60-degree rotation would represent some information. So like did the rotation of the polarization state represents different information. So we were able to produce this kind of light beams, and just encoding doesn't help. We have to get back the information, that is decoding, right? So first encode it, then encrypt it, and then decode it using the key. Okay. So we did the experiment for it also. So you can see this is the input information which we used, okay, to encode the light, and by applying all the optical experiments, we were able to get back this image. There was some little errors, okay, that is coming because of the light beam. Okay, so there are many speckles, laser speckles, and other factors. And this is the Poisson distribution of the optical field which we used here. Okay, so this experiment shows you one example that how we can use light to encode this complex information like image. One more example is the optical Zohr operation. Okay, so Zohr operation we have studied in electronics, digital electronics. Okay, right, 110. Okay, so like 0 0 is 0, and if it is alternate like 0 1, it becomes 1. Right, so 1 0 will again become 1, and if it is same like 1 1, it will become 1. So Zohr operation has basic principle that if the input is same, it will give one information, and if the input have different like 1 0, it have produce other set of result. So this particular thing we can do optically also through polarization encoding by control of polarization. Okay, so we have used 2SLF where this information is represented in terms of rotation of polarization. 0 means no rotation of polarization, and 1 will mean 90-degree rotation of polarization. So we can use polarization of light for Zohr operation. And this Zohr operation can also be used for optical cryptography. Okay, because Zohr is one of the very basic uh, technique for cryptography, even in digital domain. So we can see using Zohr operation, we can encrypt a QR code, right? And then we can decrypt it also. So then I went to Chiba University for my first postdoc. So that laboratory was had expertise in material processing applications using laser beams. So they use different kind of laser beams to produce different kinds of structures and materials, right? And they were also expert about producing different kinds of laser beams. So they were working in lasers also. So there I first demonstrated one of the technique which we used, where we used optical vortices for XOR operation. In the last slide, I demonstrated the use of like how we can use polarization to produce XOR operation, but we can also use optical vortex for implementing the XOR operation optically, everything optically, right? And I made one system there, this particular, where we used a single SLM to produce this vector vortices or other kinds of beam like optical scremions. And our aim was to produce, to control these parameters, phase, polarization, wavefront, and then create different kinds of optical fields, and then uh, to produce different structures in materials. Okay, so this one of the our recent work was published in APL Photonics. So where we have used optical scremions for producing spiral shaped structures in isopolymers. So after then I switched to another area, which is optometry. Okay, so this is the second postdoc where we did. So this is the campus of University of Houston. So our department was the College of Optometry. So that was the Eye Institute. So in the ground floor was hospital, and we were working in the first floor, which was the research laboratories. And some of people in my research team were doctors. And Dr. Bunyan Yoon, he was our supervisor. So there, uh, the problem was when we have a very ideal eye, right? So we see very clear image. So image which is formed in retina, right? So lens is nothing but an imaging system. It forms a image at its focal plane. But sometimes what happens is there is some distortions in our optical system. Okay, it can be because of the lens, or it can be because of this path. ठीक है, किसी को मोतियाबिंद हो गया, या there is because of aging effect की वजह से scattering effect आ जाता है. So there could be many things which can distort the optical path of light. So say what will happen is there will be blur effect. ठीक है, the formation of image may not be in the retina, or there could be some optical aberrations, right? So now the team was interested to first understand from where this distortion is coming, and then once we know from where the distortion is coming, we have to correct it. Okay, so for detection and for correction, what we need is wavefront sensing. Again, here we see that this shaping and sensing of optical field is very useful here in this problem also. Because what the distortion is happening is it's happening in the optical field, right? And then we have to measure the distortions in the wavefront of light. So there are many techniques through which it can be done. Some of them are also commercially available, but there was some problem in the such systems. So the team was interested in some new way to do it. So this Sack-Hartman wavefront sensor, right? So Sack-Hartman wavefront sensors are well-known wavefront sensor, even commercially available, and it is based on this lenslet array. Okay, so there are some different dense lenslet arrays, and they will create focal spots. And by seeing the displacement and distortions in focal spots, we try to judge the phase of light, and it requires some mathematical algorithms and ways to do it. But this has a problem of lateral resolution. Since we are using different lenslet arrays, here you can see in the picture, for this much area, we are getting only single point. So this hampers the lateral resolution. So we cannot get a point-to-point information here in this case. Okay, so that's why Sack-Hartman wavefront sensors can be used to measure only low order aberrations. But if you want to measure high order aberrations, then it becomes difficult. So what other ways can be done? So we were trying method which is called transport of intensity equation. This is a phase retrieval method, okay, to measure the phase of light. Okay. So see, in my complete lecture, first I showed you using how we can measure phase using polarization through retardance. Then I also showed using interferometry, and this is the third one where we are using diffraction of light. So all polarization, interference, diffraction, these all three techniques can be used for measurement of phase of light. Okay. So we are still working on this technique. We have some initial results, but there are some other restrictions or limitations. So currently we are working on it, and let's see whether this technique would produce better results. One of the problem which we are facing is the cloud effects, because this technique is based on some like mathematical algorithms, and it has phase solvers. So sometimes it converts, sometimes it do not, and sometimes because of some computational issues, there are some errors. So we are working on it. And last year I joined IIT Vilay, and now I am trying to establish this my optics laboratory here, and my objectives would be to work on these techniques, light sensing, light setting, and whatever applications is feasible here, like physiological optics is nothing but vision optics, singular optics, and information optics, and some imaging. Okay, so this is the Department of Physics. We have shifted to our new campus. This is chemistry building, this is physics building, and this is administrative building. And optics laboratory, we have got initial some of the items to play with light. Okay, and you all are invited to IIT Vilay whenever you have some free time or any internship or maybe some program, MSc, MTech, PhD. So please, you all are welcome here. So this is the night view of IIT Vilay. Very good picture. So in acknowledgement, I would like to thank all my supervisors, colleagues, seniors, students. Whatever I have shown today results, it all because of the team effort, my supervisors' directions. So everyone has contributed. So thank you to everyone. And with this, I would also like to conclude and thank all of you for listening me, and thanks organizers for this wonderful opportunity. So thank you.
Thank you, sir, for your enlightened talk. It was really interesting and knowledgeable. And now forum is open for the question and answer session. If anybody have any query or question, they can ask by raising the hands. So we can unmute that particular participant to ask the question.
Excuse me, sir, am I audible?
Yes.
So yeah, you discussed about SLMs, right? So I just wanted to know if we could combine SLMs with AI and machine learning and then use somewhere in optical neural networks. Is that possible?
Yes, of course it is possible, and I would say that many people are doing it, and even we are also trying it in our laboratory, because SLM is, of course, it is an electro-optic device. So it we create computer-generated holograms, right, using programming softwares. So now these AI tools, machine learning tools, we think that this can be very much useful for designing of digital holograms, which we can use it in a special light modulators. Okay, so this is a very, like, I think good. I would like to thank you for thinking in this direction. This is of course feasible. People are doing it, and I think it is going to be very effective also.
Okay, sir. Thank you. So that's really amazing.
Yeah. Okay.
I actually had another question too. You actually discussed about generation of optical vortex and all of that stuff, but you conducted all these experiments in lab, right? What could be the challenges when we actually generate these optical vortex in, practical applications?
Yes, I would say that there could be a lot of problems. One problem is this optical alignment, right? Because uh, this when we use laser beams, okay, so we have to use different optical elements, lenses, okay, polarizers, special light modulators. So beam alignment is always a critical thing. Okay, the researchers which we do these experiments spend a lot of time in just laser beam calibration, alignment issues. And if you made a system and someone comes and little bit of vibration can disturb it. So achieving the alignment and maintaining it, it's a challenge. Other challenge could be the this device based, like if we are using SLM, we need to continuously check it whether it is working properly or not, because these are very critical things, and it can, this phase response can be disturbed anytime, right? So these are the issues, and when we do it, when we apply it in practical real life applications also, these things have to be taken care of.
Okay,
Yeah.
sir.
Hello, sir. I am Ravi Ranjan Kumar, pursuing PhD from MNIT itself. I want to ask you something about, sir, the virtual reality. How, how do light fields can contribute in the virtual reality field, sir?
Virtual
Anything
reality. Okay.
that is related to AI?
I am not very familiar of it, but I have read some of the articles where are trying to do it. See, one of the like article which I have seen is they are using this structured light, and not particularly which I have shown in my work. There could be like different kinds of structured beams. One could be in patterns, okay, and then they are using distorted patterns, doing analysis, and they are trying to connect it with virtual reality. But I have no expertise in like virtual reality and how we can connect it. But now, since you mentioned, I am also thinking that how we can do it.
Okay, okay. Thank you, sir.
Yeah, maybe we can discuss sometime when we also when I will be
Okay,
a
sir.
little familiar with
I
some
will
of the
mail you
things.
regarding this, sir, for sure.
Yes, sure, sure. Thank you.
And Dur Durgujay Singh, I want to ask something, sir. I'm just.
Hello, sir. Sir, I want to
Hello.
ask that how is light field shaping used in telecommunication to enhance the signal quality?
In optical communication, right?
Sir,
You are,
question once again. How is light field
yeah,
shaping used in telecommunication to use the uh, to enhance the signal quality?
signal quality.
Sir, how we can use? Yes, sir.
uh, So the research papers which I have read it, till now in this use of light field shaping, they are mostly talking about increasing the capacity, like information capacity. Okay, like
Yes, sir.
most of the discussion is around that only, like how we can use lights to enhance, because light also allows parallel processing of the information, which cannot be done in digital methods, right? And also the degree of freedom is more here. So people were discussing that how we can use it for like using a single channel and producing more and sending more and more data through it. But to what was the question is asking about the enhancing the signal quality. So I am like not very sure
Yes, sir.
like it can be done in this way also. So I also have to read about it.
Okay, sir. Thank you, sir.
Okay, sir, as there are too many questions and very limited times, we will proceed further. And I will
Okay.
like to invite Sai Komal for the presenting memento and Thanksgiving. Please, Ms. Komal, proceed.
Okay, then I will then stop sharing my slides.
And if
Okay,
anybody
hello
have any
everyone.
queries,
Am I audible?
if anybody have any queries, please write to email to the mail to the sir's email ID, which already mentioned in the chat section. Please, Komal, proceed.
Okay, thank you, sir. Hello everyone. Am I audible? I just want to confirm it.
Yes, you're audible.
Okay. As we conclude this webinar, I want to take a moment to express my gratitude to Dr. Praveen Kumar, the participants, and IEEE Censors Council Student Branch Chapter, MNNIT Allahabad. Your participation and engagement have truly made this session insightful and enriching. I wanted to extend my sincere gratitude to Dr. Praveen Kumar for an enlightening presentation. Your expertise and passion for the subject matter were and your insights truly resonated with us. Your ability to explain complex technical concepts in such a clear and engaging manner made the session both informative and enjoyable. And I'm grateful for the valuable lessons I've learned from you. I would like to take a moment to extend the certificate of appreciation and token of gratitude. I kindly ask the participants to fill out the feedback form linked in the chat section of this meeting. And at last, I would like to request everyone to please switch on the webcam for the group photo as a souvenir of the event.
Thank you everyone for attending the webinar, and please fill the feedback form mentioned in the chat section so that we can get your views on the webinar and take our efforts to improve the webinar experience for the future webinars. Thank you everyone.